Today we're going to talk about the gravitational force. Okay, there's a famous story about an apple that fell on Isaac Newton's head as he was sitting under a tree. Okay, and this story is probably not true, but maybe it is. But there's a reason why we tell this story. Okay, because the story goes the apple fell on his head, and then he sat there and pondered, well, if the apple falls, why doesn't the moon fall? Okay? At this point, when Isaac Newton was around, people knew things fell down. Okay? Columbus had settled and come into the Americas and things like that. So people knew things fell, but we hadn't said, hey, well, things fall here on Earth, but why aren't they falling out of the sky like the moon? Okay? So he came up with this idea of placing a cannon high up on a mountain, okay, and firing that cannon, okay? And we've learned that the trajectory of projectiles is a parabolic path, okay? So the cannon on a high mountain would eventually come and hit Earth's surface. And he said, okay, if I fire a little further, well, then it's going to land a little further away. And even further than that, it'll land even further away. And at some velocity, when it is fired, it is going to come back around to where it started. Okay? And he said, well, that is what the moon is doing. The moon is perpetually falling towards Earth, and that is what is causing the moon to orbit Earth. Okay? Then he took it another step, and he said, you know what? Maybe Earth isn't the only thing pulling. Okay? Things orbit the sun. So the sun must be pulling on those objects. Okay? And he eventually came to say that all objects with mass attract each other. Even the very, very small objects. So my calculator has mass. I have mass. So therefore, there is an attractive force between me and my calculator. Now, on Earth, we don't notice that because it's so small compared to the gravitational force of Earth. However, if we were in outer space, we would notice it. Okay? If we were far, far away where we weren't affected by the mass of Earth and planets, we would notice this force. Okay? The calculator and I would be falling towards each other. The calculator faster towards me because I'm larger. Okay? But all objects attract each other. So here's the equation that Isaac Newton developed. The gravitational force is equal to the two masses multiplied together divided by the distance between the two centers of the object, so the center of mass of each object, squared. Okay? I'm missing a part here, but I want to explain this. So the larger, more mass an object has, the greater the gravitational force is going to be. Also, the greater the distance between the two objects, the bigger this number is, means we're going to divide by a big number, so we're going to end up with a smaller number. So the further you are away, the less the force you're going to feel. So this explains why when we're in outer space, we don't notice the gravitational force due to Earth as much. Okay? But if you have all this multiplied and divided, you're not going to get the correct units of newtons. Well, that's because there's also the universal gravitational constant, which is the capital letter G. And the capital letter G has a value of 6.67 times 10 to the negative 11. And that'll be written on our next slide. Okay? All right, so Newton's universal law of gravitation. A little recap here. All objects with mass are attracted to each other, the large and the small. Okay? However, we're only going to use this big long equation down here, okay, not on the surface of Earth or when one object is not the Earth. Otherwise, we're going to use this equation. Why? Well, we'll look at that in class some more, but basically this is a lot simpler, okay? And since we're really on Earth's surface and our mass is significantly small due to the mass compared to the mass of Earth, this equation is perfect for us when we're on your Earth's surface. Okay. Usually we use this equation, we use this universal law of gravitation when there are forces between two planets. We can use it for other things, but typically that's when it's used. Okay, the symbol is still Fg. It's the gravitational force. Okay, and then we've got this universal constant, the gravitational constant, and that is 6.67 times 10 to the negative 11th. Okay, and this is on your equation sheet, so you're going to memorize it, but you do need to remember that that is what we are substituting in here.